opening a soda can, fire extinguishers, balloons, syringes, flat tires. All of these are important in our everyday lives. But how do these things work? What is the science behind them? The Gay-Lussac's law is a gas law where at constant volume, the pressure of an ideal gas is directly proportional to its absolute temperature. Since it is directly proportional, increasing the temperature of a gas causes its pressure to rise proportionally, assuming the volume doesn't change. Think about it this way. Heating gases allows the gas particles to move faster. For example, in a container with fixed volume, the faster the gas particles move, the more times they collide with the sides of the container. This implies higher pressure. The formula for the Gay-Lussac's law is stated as P1 over T1 is equal to P2 over T2, where in the formula, P1 is equal to the initial pressure, T1 is equal to the initial absolute temperature, P2 refers to the final pressure, and T2 refers to the final absolute temperature. So, imagine this. It is a hot summer day and you and your family decided to have a road trip. While you are on the road, you suddenly feel a shake, a loud popping sound, and the car coming to a complete stop. All of you are shocked. One of your tires just exploded while in motion. This occurrence is due to the hot weather causing the temperature of the air inside of the tire to heat up. Remember what we have explained earlier? The hot temperature will cause the pressure inside the tires to increase. Increased pressure inside the tire will cause it to pop. This explanation of tires popping due to hot temperature and increased pressure concretely explains the Gay-Lussac's law. For you to better understand the Gay-Lussac's law, here are some examples you can practice on. A car tire has a pressure of 2.38 atm at 25.3 degrees Celsius. If the pressure inside reached 4.08 atm, the tire will explode. How hot would a tire have to get for this to happen? Report the temperature in degrees Celsius. P1 over T1 is equal to P2 over T2. For the initial pressure, or for P1, we know that it is 2.38 atm. For P2 as the pressure after the change or final pressure, it is 4.08 atm. For T1 or the initial temperature, 25.3 degrees Celsius. And the variable that we are going to solve, or the final temperature, is T2. First off, we are going to convert the temperature to Kelvin. So, 25.3 degrees Celsius plus 273 is equal to 298.3 Kelvin. Or, we are going to round it off to the nearest decimal place, which is 298. Now, we are going to rearrange the formula. T2 is equal to P2 times T1 over P1. Then, substitute the given variables. T2 is equal to P2, which is 4.08 atm, times the initial temperature, which is 298 Kelvin, all over P1, which is 2.38 atm. Cancel out atm. Notice that each of the numbers has 3 significant digits, so the final answer will be rounded off to 3 significant figures. Now, we solve for T2. 4.08 times 298 divided by 2.38 is equal to 511 Kelvin. But we are not done yet. because the problem asks us to report the temperature in degrees Celsius and not in Kelvin. We convert Kelvin to Celsius. We subtract 273 from the final answer, which is 511. So 511 subtracted by 273 is equal to 238 degrees Celsius. Now, our final answer is 238 degrees Celsius. For our problem number 2, before the road trip, the car was parked inside a covered area with a surrounding temperature of 31 degrees Celsius and the pressure inside the tires at 5 atm. The road trip then began, and at noon, the temperature rose to 39 degrees Celsius. Determine the pressure inside the tires at noon. For our given, we have the initial temperature at 31 degrees Celsius. We have our initial pressure at 5 atm, our final temperature at 39 degrees Celsius, and the variable that we are going to solve is the final pressure. Before we proceed with the solution, we need to convert the two temperatures to Kelvin. So, we add 273 to each. For the initial temperature, 31 degrees Celsius plus 273 Kelvin is equal to 304 Kelvin. And for the final temperature, 39 degrees Celsius plus 273 Kelvin is equal to 312 Kelvin. Still using the Gay-Lussac's law, we now proceed to solving P2. We rearrange the different variables from the original formula and will equate to P2 is equal to P1 times T2 all over T1. Now we substitute our given variables. For P1, we have 5 atm. For T2, we have 312 Kelvin, all over T1, which is 304 Kelvin. Now we cancel out Kelvin and multiply 5 times 312 divided by 304 is equal to 5.13 atm. So P2, or the final pressure, is equal to 5.13 atm. Now that you have learned about the Gay-Lussac's law, it's time to understand other concepts of the gas laws. This has been real-life applications of the gas laws.